Okay, here is a method to draw out a table with a minimal amount of memorization that covers 0 to 360 degrees. I don't recommend this method to solve trig problems because it doesn't have as much math understanding as a part of it. But here it goes anyway if you insist on doing a method that is completely rote memorization. So you're going to make a table that goes from 0 to 360 degrees, similar to the one we made before for 0 to 90 degrees. So the first thing you're going to do is you're going to write sine, cosine, tangent down the side. And then you're going to do the angles across the top, and we're going to start with the same angles that we did before, which are the special angles. Okay, and then you're going to continue on. Now you're going to continue on with 90 plus the special angles. So you do plus 30, plus 45, plus 60, and then finally 90 plus 90. And then those would give you 120 and 135 and 150 and 180, for example. Okay, and then you continue on. So this time it'll be 180 plus 30, 180 plus 45, 180 plus 60. So do you see, there's no memorizing here. It is only mathematical patterns, although it's tedious, right? 210, 225, 240, 270. Next set, now I'll do 270 plus 30, 270 plus 45, 270 plus 60, 270 plus 90. Now, if the task was to write out this table, I can understand why you would do it this method, because there's no other way to do it than to just, write it out. This would be what? 315, this would be 330, and this would be 360. Okay, we're finally done. But our task is not to write out a table. Our task is to find like the sine of 135 or the cosine of 210. And to do that, I don't really recommend this method. But I will continue on. So remember how we wrote out the insides for sine, cosine, tangent from 0 to 90. We're just going to basically continue that trend. So you remember how we started sine with 0, 1, 2, 3, 4. Well, you're just going to continue on, except for you're going to bounce back and forth between 4 and negative 4. So we'll go 0, 1, 2, 3, 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4, and then you bounce back to positive 4, negative 3, negative 2, negative 1, 0. Okay? And then for the next line, instead of starting with 0, remember you start with 4, right? So 4, 3, 2, 1, 0, and then negative 1, negative 2, negative 3, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. So we started with 0 with sine, and we ended with 0. With cosine, we started with 4, and we ended with 4. And now we're not going to do tangent yet, because remember, tangent is simply dividing sine divided by cosine, so that's trivial, right? We're just going to finish up here with sine and cosine. So remember that we're going to put a square root over every single one of these numbers, and that part of the procedure does not change, except when you get to the negative 1, make sure you put the square root between the negative sign and the number. Okay, so it doesn't go outside the negative sign. Remember, the square root of a negative number is an imaginary number, and we don't even do that in this class. You're just putting the square root around the positive number and leaving the negative on the outside. And we're going to continue doing that with the cosine values. And do you notice also that the square root sign goes over the numerator, but not the eventual denominator that we're going to write down in a minute. Okay? And as you get proficient at this method, you can take shortcuts. For example, instead of writing square root of 0, not write square root of 0, right? Okay, and then the last step before simplification is we just put divided by 2 on everything. Oops. And then you put divided by 2 here. And then after you finish this, you essentially are done with sine and cosine. You just have not simplified. And of course, square root of 0 is 0, square root of 1 is 1, and square root of 3 and square root of 3 and square root of 2 cannot be simplified. Square root of 4, of course, is 2. 2 divided by 2, of course, is 1. 0 divided by 2, of course, is 0. So you do all those simplifications, right? And when you do tangent, basically what you're going to do is you're going to do sine divided by cosine. So 0 divided by 4 is 0. 1 divided by square root of 3 is 1 over square root of 3. Square root of 2 divided by square root of 2 is 1. Square root of 3 divided by 1. And do you see I'm just ignoring the denominators because the denominators cancel out, right? So square root of 3 over 2 divided by square root of 1 over 2 is square root of 3 over square root of 1, which is just square root of 3, right? Square root of 4 over 0 is not 0. 2 divided by 0 is infinity, right? Square root of 3 divided by negative square root of 1 is negative square root of 3. Okay, and so this would be negative 1. This would be negative 1 over square root of 3. This would be 0. This would be positive 1 over square root of 3. This would be, negative 1 over, it's a negative divided by negative, so it's positive. Negative square root of 2 divided by negative square root of 2 is positive 1. This would be positive square root of 3. This would be negative 2 divided by 0, which is infinity. Happens to be negative infinity. Negative square root of 3 divided by 1 is negative square root of 3. Negative square root of 2 divided by square root of 2 is 1, or negative 1. Negative 1 over square root of 3 is negative 1 over square root of 3. And 0 divided by 4 is 0. Okay? All right. And then we just simplify, right? So remember, square root of 0 over 2 is equal to 0. Square root of 1 over 2 is equal to 1/2. Square root of 4 over 2 is equal to 2 over 2, which is equal to 1. I'm not sure if there's anything else, but that's pretty much it, right? You could do all those conversions and leave the negative signs where applicable. Oh, square root of 4. Yeah, I did square root of 4 over 2 also. Okay? How long did that take? That took 8 minutes with my explanation. So you can see it does not fit into the 5-minute limit that I have for the second phase of the exam. So you have to be really fast. Okay? After you make this table, then you would say, okay, now Mr. Tsubaki is asking me to do sine of 135 or cosine of 210 or whatever. So you're going to have to figure out some shortcuts to be able to do it more quickly, because just to make this table takes quite a bit. Okay, last of all, I want to show you how to do the radians. Okay, so the radians, there's a couple ways you could do it. One way would be to use the pattern here. So we know we go 0, pi over 6, pi over 4, pi over 3, and pi over 2, right? And when we get to 120 degrees, we know that that's going to be 4/6 pi, because this is 3/6 pi, and we added 1/6 pi, or 30 degrees, to get to 120. Okay, and then we add another 1/6 pi to get to 150, right? And then the 180 degrees, of course, is 6/6 pi, or just 1 pi. And then 210 degrees would be 7/6 pi. And then 8/6 pi would be 240 degrees. You notice I'm always skipping the 45 degree increment because it's not a multiple of pi over 6. And then the next one is 9/6 pi, which is actually 3/2 pi. And the next one is 10/6 pi, which is actually 5/3 pi. And then we skip the 45 degrees again, and we have 11/6 pi, and finally we have 2 pi, right? And now we could simplify some of these, like 10/6 pi is actually 5/3 pi, and 8/6 pi is actually 4/3 pi. And 7/6 pi can't be reduced, 5/6 pi can't be reduced, 4/6 pi is actually 2/3 pi. And I think that's pretty much it for the reducing. And then we could take a look finally at the pi over 4 increments. So this one is 1/4 pi, this would be 2/4 pi, this would be 3/4 pi, this would be 4/4 pi, this would be 5/4 pi, this would be 6/4 pi, this would be 7/4 pi, and this would be 8/4 pi. Okay, so now we filled in all the conversions to radians, but you could also do the conversion to radians by taking the original, like 315 degrees, and multiplying it by pi over 180. Okay, and then you could say, oh, this is a multiple of 15. How many 15s go into 315? Oh, this is a multiple of 15 too. How many 15s go into 180? And then you'll find out that it's equal to 7/4 in the end. Okay, so you would do some long division there, right? Time, and I haven't even simplified it yet, right? But anyway, that's one way that you could approach it.